Epicon tutorial.
Good day, listeners. We are solving a fifth order boundary value problem by Adomian Decomposition Method today. So the equation is as shown. We write the equation in operator form. Writing the equation in operator form, we have Ly equal to y prime 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 minus y prime. And then from here, our operator L is written as a g raised to power 5 over dx raised to power 5, and then the inverse operator is a fifth order integral operator, 0 to x, 0 to x, 0 to x, dx, 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 dx. So applying the inverse operator, we have L to both sides of the equation. We have 2 L inverse 1 prime prime minus L inverse y prime. Applying the boundary conditions, we represent this by A, we represent this by B. So let's represent this by B. So we say let A equal to y prime prime of 0, and B, let it represent y raised to power 4 of 0. So by doing that, we are going to have y of x equals y of 0 is 0 plus y of prime of 0 is 1 x, y prime prime of 0 is 0 plus x raised to power 3 factorial of A plus x raised to power 4 factorial of B plus 2 L inverse y minus L inverse y prime. So, and this can be simply written as y of x equal to x plus x raised to power 3 A plus x raised to power 4 factorial B plus 2 L inverse minus L inverse y prime. So by Adomian decomposition method, this is supposed to constitute our zeroth term, why this will be our recursive relations. But according to some modification made, because the bigger your y naught, normally this is supposed to be a y naught, then this will be recursive relation. The bigger your y naught, the more complex the computation becomes. So as a result of that, we can split the y naught into 2, so that we seed the smaller part as our y naught, while the rest will be merged with y1 alone. The rest part of y naught will be merged with y1 of our work. So that means we can split it here and say this will be our x alone, will be our y naught, such that we have our y naught to the x. The remaining part can be written as a recursive relation as yn plus 1 equal to ax raised to power 3 over 3 factorial plus bx raised to power 4 over 4 factorial plus 2L inverse of n equal to 0 to infinity d3 dx cube of yn minus L inverse n equal to 0 to infinity d dx yn like this. So to obtain our y1 at n equal to 0, our y1 will be ax 3 factorial plus bx raised to the power 4 factorial plus 2L inverse of the 3, the x cube, y naught minus L inverse d the x of y naught. So it must be stated here that the part of y naught that will match with the recursive relation will only be combined with our y1. So, and then when n is equal to 1, which is y2, so we have just this one, 2L inverse of the 3, the x3, the 3, the x3 of y1 minus L inverse d dx of y1. So let's quickly obtain our y1. That is, let's just obtain this. So y1 equal to ax over 3 factorial plus bx raised to the power 4 factorial plus 2 L inverse of 3 x cube of our y naught is x minus L inverse d dx of x. Our y naught is x. So that means from here, we are going to differentiate x 3 times, which will give us 0. Here we differentiate x once, which will give us 1. So with that, our y1 gives ax raised to the power 3 over 3 factorial plus b x raised to the power 4 over 4 factorial plus 2 times 0 minus L inverse of 1. And then to simplify this, we're going to have ax raised to the power 3 over 6, 3 factorial is 6, b x raised to the power 4 over 4 factorial, which is 24, minus our L inverse is a 5-fold integral operator. It means we are going to integrate 5 times. So integrating 5 times, 1, 2, 3, 4, 5, integrating 5 times, our y1 will yield ax raised to the power 3 over 6 plus bx raised to the power 4 over 24 minus x raised to the power 5 over 120. So this is what we obtain for y1. You can go ahead and obtain y2, but we are going to collect our results here. So our y of x now will be y naught plus y1. So that will be our y naught is x plus ax raised to the power 3 over 6 plus bx raised to the power 4 over 24 minus x raised to the power 5 over 120. And so this is our y of x in terms of a and b. So how do we now obtain the values of our a and b? So we obtain that by applying these boundary conditions at x equal to 1, y prime at x equal to 1. So let's take the first one, applying the boundary conditions, y of 1 equal to 2, that is at x equal to 1, y is 2. So from here now, y of x equal to 2. So anywhere we see x, we replace it by 1. So we have 2 equal to 1 plus a over 6, a over 6 plus, because our x is 1, 24 minus 1 over 20. Simplifying this, we will obtain A over 6 plus B over 24 equals 121 over 120. Let's refer to this as equation 2. Equation 2. Then we also apply the other boundary conditions. The boundary condition y of 1 equal to 1. That is, when x equal to 1, the y, the x equal to 1, 2. So that's what that entails. It means before we can apply it, we have to differentiate this equation asterisk like this. We have to differentiate this equation. So differentiating that, our y prime of x is going to give us 1 plus 1 over 2 a x squared plus 1 over 6 bx raised to power 3 minus x raised to power 4 over 24. So if we now apply our condition x equal to 1, when the y dx is, so the y dx is 1, then we have 1 over 2a plus 1 over 6b minus 1 over 24. Simplifying this will give us a over 2 plus b over 6 equals 1 over 24. We refer to this as equation 3. Equation 3. So we are going to solve equations 2 and 3 to obtain the values of a and b. Solving equations 2 and 3, our a will be 479 over 20, and then our b gives negative 358 over 5. So we are going to substitute that into this equation asterisk. So we are going to substitute our a here, our b here. So substituting that, our y of x equals x plus 479 over 120 x raised to power 3 minus 179 over 60 x raised to power 4 minus 1 over 120 x raised to power 5. This is the solution of the 5th order boundary value problem. Of course, we can obtain more terms so that if the exact solution exists, it can converge to the exact solution. Thank you for listening.